Good day, everyone. I am Joaquin Cruz Maclang from the University of Southeastern Philippines, here to present to you all HomePiano, a monocular augmented reality piano using fiducial markers and machine learning for contact inference. So here in the Philippines, piano accessibility still remains as a main problem, as piano prices ranges between 3,000 to 300 US dollars, whereas the average Filipino monthly wage costs around 350 US dollars, not taking into account the average taxes, bills, and insurance a Filipino has to pay. Although there were also technological advancements to help reduce this curve, such as mobile and computer applications, this medium still lacked the direct key press feedback of a physical keyboard. Moreover, augmented reality type still forces users to rely on tracking projected landmarks such as 3D objects and text over a physical piano, which results in users still learning incorrect hand placements or incorrect hand gestures and finger placements. So for our study, we wanted to focus less on projection and more on allowing the user to see a tangible printed piano on the other hand, and allow the model or computer to focus on processing that alone so that the user can instead focus on playing on the piano that they can see. So for that, the related literature here notes the different types of challenges. So for piano localization, although Aruco 3 was seen as the most versatile model for spatial tracking through lightweight CNN models, there are also markerless strategies such as SLAM and BIO. However, these are seen as computationally intensive and rely on high-quality sensors. So for the sake of portability and affordability, we will stick to Aruco 3 for piano detection. Second is contact inference. Although the following literatures here have noted to use a vertical coordinate system, others focuses on the shadow cast and the expansion of the fingers width. The first two, such as from Isagawa and Yi, requires the use or are light dependent and also require good and high quality sensors. On the other hand, Hiranaka utilized it for a third person perspective, which allows a computer to see a 3D image or the y-axis or z-axis rather from the distance of the finger to the paper itself, whereas this paper will focus from a top-down perspective. Thus, this made us authors to focus more on a more unique kinematic feature set that tries to analyze the speed of how fast the finger moves throughout the image or throughout the video. Third is perspective normalization. Given that we'll focus more on kinematics, distance will become a problem. Thus, using homography as a pre-processing technique, we can then utilize this not as a projection, as used by Hiranaka, but rather to ensure that the features extracted for the kinematic velocities will become normalized for the model to perform better. Overall, we aim to create a portable experimental AR piano using a monocular camera and a machine learning classifier. Specifically, first we want to develop a top-down AR piano that detects hands, pianos, and key press actions under 120 millisecond inference latency. Second is to generate a feature set robust enough for key press detection, then use that feature set to generate or to train and compare a RF and SVC classifier, and these will serve as our models that will predict whether we press the piano or not. Then fourth is to design a detectable piano paper prototype with Aruco markers and 7 white keys. From there, we have designed the following paper piano, which utilizes two Aruco markers situated at the upper left and right corners. Now, the data used to train our model was collected by recording 8 students to play the designed paper piano shown earlier. And it contains two phases as seen over here, and each phase is played under different beats per minute. So each phase in the beats per minute aims to help simulate the constant or static key presses and key presses made under different types of speeds. So this will help create the kinematic velocities we hopefully need to train our model for better contact inference, thus the need for two different phases each hand. Next, from the extracted videos, we'll then push them through the home piano pipeline, which will focuses more on the feature extraction and contact inference. So first, this is an example in the image shown here was during our data collection process, which is in phase 2, played under 60 beats per minute. So first, we capture the image, detect the local markers, and form the border, which is the green box you can see over here. We'll apply homography to help fix the orientation of the piano as well as the hand position. So it will now, the rectangle will now, or the border will now form a near 90-degree, perfect 90-degree angle. Next is to apply media pipe hand tracking to formulate the hand landmarks. Then we'll now focus on the kinematic feature set. So we utilize feature engineering here as to analyze the movement of the finger using pixels, or specifically displacement. So the movement from one landmark to the other. So utilize Euclid's displacement formula. So it's the distance from one point to the other to know the distance traveled from one frame from the previous frame to the next frame. Then from there, we'll analyze the different types of displacements to get the velocity, how fast it has been moving across different frames, then get a smooth rolling average. We utilize this feature as well, as it is essential for us to understand the movement from different frames across 5 frames, 10 frames, and 15 frames, because there may be a chance that the person may be moving extremely fast for the recent 5 frames, or moving extremely fast for the previous 10 frames. And as machine learning models such as random forest and support vector machines or classifiers are unable to memorize or analyze previous entries as compared to deep learning models such as recurring neural networks, these smooth rolling average velocities hopefully allow the machine learning model to have the peak from the past or the previous frames that has been fed into the model. So from the kinematic features extraction or the feature engineering, we have now generated the following dataset features. Overall, the features utilized for the model are the fingertip, so either the index, all 5 fingertips. Then tip to tip up to MCP to wrist are basically joint to joint distances from here to here, here to here, here to here, then here to here. Applied for the remaining fingers as well. Next is the displacement, which analyzes the distance from your example from this image. It is the distance traveled from your finger from this landmark to this landmark using the Euclid's displacement formula. Next is the V size and V displacement. So V size is the smooth rolling average for the size of the joints over here. It is an aggregate. So we'll take this, the sum of this, get the average, and then store it over here for the past 5, 10, and 15 frames. V displacement is the same, but for displacement. Also, to keep in mind, the smooth rolling average also saves the most recent velocity. So it functions similar to a queue, where it will only take the most recent 5, most recent 10, and most recent 15 frames, just for clarification. Then all of these features will be fed into our machine learning model for key press detection. Then finally, for the dataset extraction, we utilize LED ground truth extraction. So as OpenCV is unable to analyze audio data, we wanted to create instead of visual cues. So we utilize an Arduino LED setup that utilizes a capacitance sensor. So for better visualization, it functions like this. If you press the aluminum foil, it will create a change in capacitance that Arduino can detect. That change can then lead to a person or a specific LED to light up. So integrating that to our dataset, we will then just track if the LED has lit up. We can also do that by focusing on the RGB image or RGB values. If the RGB value reaches 225, we will then save that as a key press, then find which finger is hovering over that specific key. So we'll set that fingertip to is pressing. I've also forgot to discuss also. Distance is the distance from the camera to the piano. Is pressing is discussed from the LED ground truth extraction. Then finally, previous action is similar to is pressing, but it is the state from the previous frame. So for example, in frame 1, is pressing is true or 1. Then in previous action, or when you come to frame 2, previous action will now be set to 1 as well. Now, for the dataset distribution, we are able to extract a massive dataset of around 1.69 million entries, with hover taking up 94% of the entire dataset, whereas press takes up around 6% of it. The model is now trained under stratified k-fold and group shuffle split to prevent data leakage and help in training the models with an imbalanced dataset. And note, both models are trained using both balanced and imbalanced data for comparison. As based from other literatures, we believe that if we want to, we believe that we'd like to experiment with this to see whether the model will become less prone to, what's the right term for that? The models will become less prone to misclassifications or more confident when it comes to saying that a person has pressed on the keyboard. Moreover, we have utilized Optuna TPE for our hyperparameter tuning, which is a model that functions similar to Bayesian optimization that smartly searches for the best parameters based from the past results or iterations. So seen in the PowerPoint are the parameters that is being tweaked for the SVC and random forest model. Moreover, we utilize the following evaluation metrics for classification tasks, which is accuracy, precision, recall, and F1 score. Now, for the results and discussion, the imbalanced models were seen to have a more dominant or a slightly higher performance as compared to the underbalanced dataset. Moreover, SVC was seen to have the highest overall, with a minimum 0.5 to 2% better performance, with a 98% accuracy and 89% F1 score. So this shows how the model is still not as accurate when it comes to differentiating key press and key hover actions. Moreover, the underbalanced model was seen to have a higher recall for this and has a closer or has a near close performance with the imbalanced dataset. This means that the underbalanced model has a high generalizability as well. Now, after training the model, we noticed that we have reached or surpassed the 200 millisecond delay, which, as mentioned by the source over here, is what causes the performances to slow down or constantly change in tempo. And further analysis, we noticed that the milliseconds per frame reaches around at minimum 143 and at most a staggering 296 milliseconds. After exploring the model latencies, media pipe takes over around 30 to 40 milliseconds. Aruco is 50 to 140, and the ML models are mentioned as such. When amounted to all of these, it is most likely probable that the performance of each model or the entire pipeline will exceed 120 milliseconds. Following the delay, this have introduced a problem during the live performance as we notice that the models are unable to detect key presses. So further analysis mentioned that there is a problem called temporal cue desynchronization wherein the models are trained over a dataset that is trained under or extracted from 60 frames per second, and we're now feeding the model data around 5 or let's say at minimum 3 to 7 frames per second. This causes problems when it comes to our displacement features because from different frames, the smaller the frame, the smaller the displacement, and the smaller the traversal for each displacement. However, the larger the frames, it may be detected that the one landmark from here can be situated over here, which then exceeds the classification of the model, which may be causing it to automatically set the value for that as a hover action, regardless if you're pressing or not. Further analysis also noticed that due to the desynchronized velocities, it causes the predictions of hover or predictions to lead to previous or sorry, it leads the velocities or the predictions to become zero or a hover action, leading to previous action also being zero, further making the model to lazily predict key action as a hover because for the exploration in the feature importance, previous action is seen as a constant important feature for all the models. Thus, we wanted to retrain the models without it. Further analysis show that so what was further analysis show that the RF and SVC, the RF was seen to have a lower accuracy and is even reaching lower than random chance, whereas SVC also lowered to around 80 to 70%, although it has a much better precision and recall and key press differentiation. Feature importance analysis also mentioned how random forest is joint distance reliant, massively, especially for the depth to depth, whereas the support vector classification focuses more on a balance between velocity and joint distance features. Finally, comparing the latency of the newer trained models, the RF has a lower latency and the SVC has a latency that almost double. This is because of their new parameters of RF having a higher number of estimators and the new SVC having a more stricter classification or more stricter regularization, which makes classification much more faster. Moreover, the same retrained model still shows the same issue of unable to detect key presses. This may be also due to, again, temporal cue desynchronization. So overall, our contributions is that we have developed the following AR piano design using the mentioned tools to create a monocular piano functional to a laptop and cell phone as our sensor. Moreover, we utilized an ML-based inference for key cross differentiation. Then we developed a feature set using phalangeal compression ratios, top-down piano distance, temporal displacement as MAs. Then we also utilized a hardware synchronized dataset using an Arduino LED capacity touch protocol. Then finally, our study can now then be used as a potential benchmark for false positives and offline performance. Lastly, for our future work, we intend to include or suggest the inclusion of black keys that it is probable as it only requires coordinate detection. Then engineer other possible feature sets for key press detection that helps make a model better infer whether a person is pressing or not. Next, develop better low latency models for key press detection, piano localization, and hand tracking. Else, if that seems hard, we can then instead create a method to normalize hand movement and size changes in a case for frame drops and frame rises. Finally, is to increase the diversity of the dataset. Lastly, before I end the study, we'd like to acknowledge that this research was made possible through the generous support of the Department of Science and Technology, Science and Education Institute. Moreover, we'd like to thank the 8 student volunteers who helped us in the data collection, our families, and as well as Almighty God for their bottomless support and blessings. That is all. Thank you for listening.